Recording has started.
Okay, so thank you so much. So I'm just going on to the slideshow mode, Prakash. So just in case you're not able to see
Yeah,
the screen, please do let me know because
yeah,
sometimes we have these issues.
yeah,
Okay, I'm in the full screen mode. Am I visible
yeah. We are, yeah, you're
and
visible.
audible? Yeah,
Absolutely.
yeah. Thank you so much. So today we are on session number 17-18 as part of our small quest to go through this quantum computing fundamentals. So we call this as QC 101. It's the basic starter course, and today I guess would be the last session. We're going to more or less wrap up most of the topics today. And we are on the topic of quantum computing algorithms. And last week, we had discussed about quantum phase estimation. Prakash had a very good session to specify or identify means by which we can just do a phase estimation. Before I just get on to the small demo, let me also give a couple of meaningful insights as to why we do really require this. Most often, what we tend to do is any input which we need to be handled over to a quantum algorithm, that input we try to encode it, the input values we encode it using the phase components, right? So we have what is called as a quantum phase encoding that happens. And the input, once it is put up into one form of a phase, and if it is given to a quantum algorithm or a quantum circuit, the quantum circuit will process that and it generates an output once again. And the output one, how do we read this output? The simplest way to read the output is look at the output and then try to estimate what is the phase. Right. So once we use this phase estimation as a means by which I can identify the output generated by a quantum algorithm, then it just gives you a very good idea as to what exactly was the input and how did this input get operated upon by the algorithm. So that is one of the reasons why this phase encoding and phase estimation are pretty very important. You pick up any type of a domain, maybe image processing or maybe signal processing, or you talk about maybe even machine learning algorithms like k-means and stuff like that. Most often the inputs are encoded in the form of a phase representation. So quantum phase estimation happens to be pretty very important. And what exactly is the aspect that is used out over here? Once again, we will be using the QFT. The QFT block happens to be now once again the bread and butter for most of these algorithms to run. So today, what I'm going to do is very quickly, I will take you through the IBM QuizKit way, and then we will quickly set up the circuit for QPE, and then we will see the working of it. Okay. So that would be my topic, and post that Prakash would move forward, and then he will introduce this Shor's algorithm per se. So when you look at the IBM QuizKit implementation, this is the implementation that is also there in the book. And what is being done is something like this. I have the QFT, which is essentially used for the aspect of trying to transform the input down and doing a Fourier transform on this. And the moment I do the Fourier transform on this, typically I can do a estimation of whatever are the most important phases in the sequence of the outcomes which I can see. That is basically a very, very simple way of looking at the role of the QFT out there. And obviously, so this centerpiece QFT happens to be the most important thing. So what I do is in this small example circuit, I need to introduce some phase, right? If at all I want to measure that phase, let me just introduce the phase. And the simplest way to introduce the phase is using a, let's say, I can typically put in uh, a controlled gate out over here. And this particular control gate is the control phase shift gate out there. So I just have a phase shift here and that is introduced. Rather than directly introducing that, I just have a control, and that particular control is done through this particular input out over here. So when this input is 1, then it will be introducing a phase shift, and that particular phase shift is what I'm going to subject it as an input to my QFT, and using the QFT I just measure the outputs. Right? That is a very, very simple pipeline. right? So what do we have in this implementation? Normally we have these inputs which are given at two different forms. One is what is called as a C register and the B register inputs, right? C register inputs are the one which are actually the inputs which I'm interested in, and the B register input is the one which will be the value which I'm going to be observing. So I will just take the value of the B register, and this is what I need to estimate. And to estimate this phase, so let us assume that I use a NOT gate here. And the moment I use a NOT gate here, if I just observe the eigenvalue at this output, now it should be equal to -1, right? That is a NOT gate. Now, that value will have to be inputted out over here through this sort of a phase introduction. Okay? So I typically will use this as a means by which I introduce a phase shift. This phase shift is introduced here, and that is what is being measured and estimated out of here. So let us understand the way this is going to work. Fine. So I'll just go through Quiskit and we'll come back to this particular slide after I show a quick demonstration. So I'm just going to my account here, and this is typically my composer, and I require typically 3 bits out over here. So I will have a Q register which will have 3 bits. So I'm just adjusting that here. Okay, and then I'll bring in the individual required components which are needed. So first and foremost thing I'm going to bring in would be, let us say, this the NOT gate. The NOT gate will be used as a control element out over here. Fine. So what I can also do is, I can just put up small barriers here. So this is a barrier which allows me to keep these stages separately. So I just put the barrier, adjust the barrier, and make the barrier go along the entire lines of input. Fine. So, and I also now need to put these two input lines into superposition. All right. So for that, I just bring this is a combined superposition. So this is my superposition. It's something like a H2 gate, right? So I just bring in the two Hadamard gates. So I have that into superposition, the H2 gate. And now I need to get the controlled Z gate, right? The controlled Z gate is something out over here. Where is that? Where is that? I bring in that Z gate here. Now this is a normal Z gate, so I have to convert that into a control Z gate. So once again, I click on this particular properties, add up the control, and the moment I add up a control, it just typically defaults to 0. So you can specify whichever bit should be the control, you can specify it out over here. So I got the control Z gate, and we also put up an identity out over here so as to keep all the actions in sort of a sync. Okay, so that is what it is. And then once again, I'll put up a small barrier because that more or less completes the second module or second phase or second sequence of activity. So I just extend, right? That is the second part of it. And now I am going to bring in the QFT here. So what is the size of the QFT? Here we are talking about these 2 qubits, right? So I'll have to bring in a 2-bit QFT, right? So it's a 2-bit QFT. So the 2-bit QFT will have one, what is that? The P gate with a -pi/2, right? So it will have Hadamard P by P gate with a -pi/2, and then the H gate, right? So if at all it were a 3 qubit, then there would be 2 stages, right? 2P H and then another 1P and a H. So we have seen those sort of QFT implementations. We have also seen the 3 qubit and a 4 qubit implementation also last time. So here I am bringing in only a 2 qubit. For that, I require to start off with a Hadamard gate here, number 1, and then we will get this one polygate, and that is typically going to be -pi/2. So I'll go out over here and then make that to -pi/2. So that is -pi/2, and this has to be controlled by this line. So how do I control that? So I just go over here and then add a control, right? A control will be here. So I got that typically the controlled. And now I'm going to put up another hammer here. Fine. So that more or less completes the QFT. But remember, at the end of the QFT, you also require the very important element out over here, which is your swap. So I need to swap these elements. So let me once again take these values. Sorry, where did I put this? Yeah, that is a swap. Right? So now this entire bunch of gates now completes your QFT. So I'll once again put up a small barrier here, and that barrier, okay, will create a small block-like scenario, and then I now need to do a measurement. Now remember, when I want to do the measurements, I'm going to do the measurements of the 2 bits. Right, these 2 bits out over here. So remember, this is Q2 is your MSB, this is your LSB. So I just have to measure. This is the first measurement, and this is my second measurement. Okay, and as I complete that, what do I get? I should be getting out over here a 101, 100, correct? It is got that, and this is my output. So let us try to interpret what this basically means. Okay, so if at all I look in my Q sphere, I just get this current state, or from a state vector point of view, it is a 101. But from a measurement, if at all I look at that, the probability is I get typically 100, 100. Now in this, I'm measuring only the least most significant 2 bits. Now these most significant 2 bits are pretty very important, and using this most significant 2 bits of a measurement, which we call it a value k, I can now estimate what will be the phase with respect to this phase that got introduced out over here. Right, whatever we have introduced out over here is typically a phase value, which is I just only have flipped out over here. So this typically would be a having an eigenvalue of -1. So it is like e raised to the power of minus j omega naught and stuff like that. So this will be eigenvalue of -1. So how do I get that? There is a very pretty simple formula by which you can just convert these 2 bits which you have measured into the phase. Okay, so that is exactly what we need to do, and that will justify, okay, whatever is my measurement for my phase here. So remember and note the fact that my output that is measured is 100. So which also means the fact that the most significant 2 bits will be 1 and a 0. So 10, those 2 bit values will be equal to 2 in decimal form. 10 is equal to 2 in decimal form. So how do I use this information? Right. So coming back to the slide. Okay. So let me come back to the slide out over here, and let us put that values into our formula. Okay. So if at all I just look at these 2 bits of observation, now these 2 bits of observation will be equal to 1 and a 0. And that particular value 1 and a 0, which is called as the C register observations, we call this value is equal to k. And that particular value of k is equal to 2. And I plug that value of k in this particular phase estimation formula. So remember, from my input side out over here, it is 2 pi psi. Why is it 2 pi psi? Because that is the value depending upon this particular introduction of my phase. And what am I observing now? The resultant is estimated to be 2 pi k over 2 raised to the power of n. And what is this n? N is the number of bits in my C register. So the number of bits in my C register happens to be 2. And because of which I get 2 pi into 2 divided by 2 raised to the power of 2, that will be equal to pi. And this pi is estimated as the phase for my input, and that phase of the input is also the same, because we have just flipped the input. We have introduced a flip out over here, and this is a controlled let's say phase gate, controlled phase, and that will have an eigenvalue of equal to -1. Now what do we mean by using these 2 bits? If at all I use more than 2 bits in my C register, I'll be now getting a better opportunity for me to measure the phase with a higher resolution. So remember, now I've got n equals to 2, and my observation are the most significant 2 bits. And what are the combinations which I can get? It will be 0, 0, 0, 1, 1, 0, and 1, 1. So which also means the fact that the phase that I can estimate could be any one of the 4 phases. Whereas if at all I use a C register which has got 3 bits, now what I can typically get will be a higher resolution. With 3 bits, I can get 0, 0, 0, 0, 0, 1, etc. all the way going up to 1, 1, 1. I can have 8 different phase values which I can estimate. So this is typically once again a design choice as to how much of a resolution you would like to introduce, and that is what is done by introducing more number of bits, higher order number of bits into your C register. So here is a small circuit which is there also in the book. I did not try it out though, but this is something like this. The estimated value typically will be dependent upon this formula. K is what you are measuring and N is the number of qubits which you are using in your circuit. And as I told you, if at all you use more number of qubits, that will enhance the resolution. So with the 3 qubits, obviously now what is the additional cost you're going to pay? The QFT which you're going to plug in will not be a 2 qubit QFT, but it will be a 3 qubit QFT. So this is a small example here. So once again, we have got the input and I've got basically the flipper here, right? I'm introducing the phase, and starting from here, this is the stages. Coming up to here will be the 2 stages of the 3 qubit QFT. And once again, I'm going to do the measurement, and this time I'm going to measure how many bits? 3 bits. And this measurement is what I can take. In this example, I can just see it will be 100, 100. I can take it and then try to plug it in out over here. Once again, that will yield to be a value of the same thing. Okay, so depending upon to what degree of a resolution you would like to measure the phase, you're going to enhance the size of the QFT circuit, and correspondingly you're going to also increase the number of bits in the C register. Okay, so that is what I just wanted to demonstrate and then show it to you. And uh, uh, Prakash, if you can just take over from here, you can just get on to this topic of maybe a brief introduction to GCD.
Yeah, Gokhale,
Yeah,
can you move the slides for me?
yeah, I can move the slides for you.
Oh,
Or you
so
want me?
just
Can I
no,
want me to stop sharing? I can do that also.
no, you don't stop sharing because I don't want to disrupt in between.
Okay, fine. Go ahead.
Just go silent and
Yeah, I'm
on
just
the slides what I'll put in the chat window. I'll say next.
one second. Let me just do that. Prakash, you can just say next, and then I will automatically move to the next slide. Okay, because I don't think I can see the chat window because I'm presenting, right? So my screen
No
goes
problem.
full.
Just make sure that you go into the
Yeah, I'm going.
presentation. Hi everyone. Thank you for looking at the uh, quantum phase estimation demonstrated by Professor Gokhale. It was really very important for us to be able to understand, because this quantum Fourier transform is used everywhere for anything and everything almost, because the reason for that being most of the work in rotation is unitary. So after you get the magnitude, even you can get with matrix. How do you measure the phase? Because the phase, periodicity, all that matters. So with that, I will move on to trying to move on to what you call Shor's algorithm. Now, before I move on to say that Shor's algorithm or anything, first let's understand that we are looking at a factorization of a large number. And to do that, let's just take two natural numbers, let's call it A and B, and we can do a computation of highest common factor or greatest common divisor. They are the same thing. HCF and GCD are same thing. And that is, if you have two numbers A and B, GCD of A and B is represented as G, as shown in the equation there. So if you go and look at the greatest common divisor G, which is the largest number that divides both A and B without leaving any reminder. So there should be no reminder. So this is also called HCF, as I said. So let's take G equal to GCD of A comma N. Instead of doing A, B, let's say A and N. Now you can call GCD of A, B or GCD of A, N. The important thing is, because A and N, which is the second number, both are multiples of G. That is, if A is equal to mg and B equal to ng, then the common factor between mg and ng is G. And that G is the one which is defining as the greatest. G is there is no number other than G. There is no number greater than capital G greater than smaller g, which is if it is true, then G is the greatest. Lower g, smaller g is the greatest common divisor. Why that we put is because if you have some number where you have got smaller numbers which is factoring able to factor a number, then that's not what we are looking. We are looking for the number closest. So it should be almost be half at least. That's the assumption. Or we put it any so big that when you do a GCD of A comma N, A is the smaller one, N is the larger one. N is what we are looking at. Y n, that will come later, but uh, the A and B are the two numbers in this case just to compute. But when you are looking n is the largest number which you are trying to get, for which we are getting the corresponding greatest G, which is the highest common factor between the for the number n. Okay, bit of a confusion, but let's just take an example. So you have 1386 that can be factored as 2 into 3 into 3 into 7 into 11. You have to assume that this is already computed, but that is the correct number. And you have got 3213, which can be factored as 3, 3, 3, 7, 17. So if you do a GCD of 1387 and 3213, you can see what are the common factors there. 3, 3, 7. Those are the three which are the ones which are common between the two. So 3 into 3, 9 into 7, 63. So 63 is the greatest common divisor between number A and B, or you can say highest common factor between A and B. So that means what? The prime factor 3 repeats 3 into 3 divides both, right? So repeated 3 times 3 times 7. So all we are trying to do is how do we find? So if two numbers have common prime factor, no common prime factor. Suppose we did not get this 337. We just got one prime and another prime. If there is nothing common between the two, then you will not be able to get anything. You will greatest will be 1. So 1 into 7 and 1 into 3, 7 and 3, they are prime, right? But you don't have anything common. So the only way greatest common divisor for them is going to be 1, which is an empty product. So you may get empty product. That's a possibility. But how do you do if you have multiple numbers? Example. So GCD of A, B is G equal to GCD of A and B. So if I have GCD of A, B, C, how do I compute? So GCD of A and the GCD of B and C, you can multiply, and you can do all these permutation, what do you call, association and dissociation, or whatever commutative types. GCD of A comma B into C, GCD of A comma C comma B, and all that. So you can do for n number, 2 number, 3 number, 4 number, n number, infinity. Let's do a procedure for GCD calculation. Now let's take one more number, and that is 1071 and B equal to 462. Google, can you click on this GCD here? Click on GCD. Click on GCD. Yeah. So if I have a number, normally how do you do highest common factor or greatest common divisor? You take this B, divide by A. Then how many times? Let's say 462 into 2, you get 924. Then balance comes out 147. So now what you do? You take the 462, which is the A number and B number here. So A you bring in, and then 147 you want to divide 462. 3 times you do, you get 441, and 462 minus 441, you get 21. Again, you do one thing, you take the 147, which is the last remainder, and put it here. So previous remainder was brought here, last remainder is brought here. So then this 21, you divide 147 into 7, you get 0, 0, 0. Basically, that means you are able to get a modular which comes out to be 0. So we can go back now. So this is normally we teach our kids when they do the HCF or GCD calculation, correct? You just divide. So the same thing can be put here as 107 is 2 into 462 plus 147. Then 462 is 3 into 147 plus 21. And 147 equal to 7 into 21. That means it is 0 now. So this is tabulated as step 0, 1, 2. Step 0 equation. 107 is Q0 into 462. So Q0 here is 2. Q0 equal to 2 and R0 equal to 147. That is, remainder is 147 in this case. The second remainder is 21. Third remainder is 0. So what we want is, if we end up in 0, that means we know that we have got the right numbers. So essentially, we are trying to have quotients and reminders. So idea is to somehow factorize these two numbers and find what is the most highest common factor or the greatest common divisor. And so we take steps. So why I am going into this is, what is the algorithm? Algorithms is nothing, step 0, step 1, step 2. So steps are k steps, and there are quotients and there are reminders. And whatever we get at the end, that is what it should come to 0. If it comes to 0 means we have got the right division, right? So determining a GCD is easier part. That is, we can do, of course, this is easier part, but this is a easier part in the sense that if you are given the numbers, you can always determine whether there is a whether they are factorizable, and if they are factorizable, are they prime, and what is the greatest prime, we can always determine. But this is only one part of classical part of the Shor's algorithm. We'll see what is Shor's algorithm. So let me give you some next. So what we are doing here is, we have overview of Shor's algorithm. So we have a number which is huge, billions. That is 3, 3, 6, 3, 9, 3, 12, 3, 15, 3, 18, 3, 21, 22 digit number. So if we have to factorize a 22 digit number, they will approximately split in 12, 10, right? 12 digit and 10. You can see that 1, 2, 3 into 4, 12 digit, and other one is 10 digit. So if you have 22 digit, it splits into 12 digit and 10 digit number. So what is the observation in this when you want to do, if given n, which is a product of two prime numbers p and q, let's say, then some a, if you start with some baseline a, let's say we call a, and that is divisible by either p or q, right? It is not divisible. If it is divisible, then we are no meaning, right? Because if a is not divisible by p, obviously, so example we'll take down. So if you have a number 15, right? Because it is simple to understand, 3 and 5 are the factors for that. We know that. Now, what is the goal of us? If you have 2 as a number and n is the number 15 and 2 is the number we chose, let's say. So our a we chose as 2 and n is 15. So now, how do we reach 15? So what we do, the step, what we are doing, the same step we are doing as a raised to k, whereas kth step is 0th step. If it is k raised to 0, then 2, you can't divide 2 by 15, so you have 2. Then 2 to the power 1, 2 to the power 2, you will get 4. 4 again, you can't divide by 15. 8 again, you can't divide by. So your remainder is going to be 2, 4, 8. Now once you reach the fourth, 2 to the power 4, 16, if you divide by 15, your remainder is 1, right? So the remainders is what we are computing here. That is a raised to k mod n is nothing but we are computing the remainders and putting it 2, 4, 8, 1. Then we go to 32. When we go to 32, that is 2 to the power 5, 32. So if we divide 32 by 15, you are getting a 2 balance. Again, you go 64, you get 15 4s are 60, you get 4. So this will keep on repeating 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1. What it means, the repeat factor R is 4 for a number 15. And so this is what we need to determine. Once you find 4 as the factor, then suppose we didn't know 3 and 5. We just have to say that whatever 4, can it divide the number, whatever your n is. In this case, we know it. So let's say 3 minus 1 and 5 minus 1. 3 minus 1 is 2. 5 minus 1 is 4. 2 into 4, 8. So the number repeat factor can divide whatever is your p minus 1 and q minus, whatever your pq, because we said n is equal to 2 prime factor p and q. So p minus 1 and q minus 1, when you take and you multiply, that will be the one which will be divisible by r, which is the repeat factor. So repeat factor is 2, 4, 8, 1, 2, 4, 8, 1, 4. 4, after 4, the pattern keeps periodically repeating. So when you divide the p minus 1, q minus 1, even if you didn't know p and q, you should be able to divide. If you are able to divide, then we have reached the correct period. If not, then we'll have to repeat. So once we know the period r, it's not too hard to find n's prime factor, because p and q, we know that p minus 1, q minus 1, whatever repeat factor is there, r can divide that, and therefore we can determine what is, because we know n, we know p minus 1, we know q minus 1, and it is also a multiple of 4, then it is easy to figure out. But determining r is the harder part. Rest can be done classically, but finding r is the most time consuming for a classical computer. Next. So what we will do is, we'll do a inverse quantum Fourier transform to find the period. You know that periodicity we saw in the QPR also case, right? In the quantum phase encoding measurement, right? What we saw when we tried to do QPE, estimation, that is quantum phase estimation, we saw we had a circle. Same we had previously when we did a QFT. You have a circle and you keep rotating the vector counterclockwise. And when you have, like we had some, what you call, nth root of unity. And when we did the quantum Fourier transform, I had taken a 12 and divided the circle, unit circle, into 12, and we said that each one is 30 degree. So in this case, if you are going to get a 22-digit number and all that, where you got 10-digit and 12-digit, you are going to get 2 to the power maybe 10, maybe 2 to the power 22. So 2 to the power 22 and all, that is the level where we'll have to have so many what you call qubits. So every power will require a qubit. So if we do 2 to the power 22, then we'll require 22 qubits, right? Or even more than that, because we have to do the ancillary portion also, like we did Mn. If you remember, in the QFT we had M and N. N were the actual ones which we had used, and M were the ones which were ancillary. And our MSB is your what do you call, the uh, N bits, and LSB was your M bit. In this case, like what Gokhale had explained previously, phase estimation, we had B register and C register. So we were operating on the B register, whereas we were using this control from the top. But it can be other way around also. So anyway, more important for us to is we have to use the inverse QFT. Rest of that is classical, and we have to make sure that algorithm has some termination, because if it goes random for infinity, that's not what we want. So once we know that first rotation and second rotation, we'll know the period, and that is what we need to figure out. Next slide. So now putting together the classical as well as the quantum portion. So what we do is, n is the number to factor, and we choose a random a which is much less than n, and then we try to see if it is trivial or not. If it is trivial, we just ignore it, because if you have 15 and 15, and if I give 3 and 15 and 15, then what? 15 divided by 15 is 1. First shot itself, it is a trivial. So you cannot chase the number n that way. It has to be other than that. Like example, I can choose a number 3, 15. Then at least they are not same. So that means you will have some kind of a periodicity, and that periodicity will be determined. That's why even though this is GCD a comma n equal to 1, all we are saying is a and n by a are factors of n, then it will not work. So therefore this is bit confusing, but remember, all we are saying is if you have number same number 15, 15, you get 1. What do you do with that? We can do nothing. But we want periodicity. So if I put 315, then I know that there is some periodicity. Whatever it may be, smaller, bigger, that we don't care. So as long as it needs to be periodic, and it should be odd. If you have an even number, what's the use? Because anyway, it is not a odd number. It cannot be a prime number. It has an odd number. It has to be odd. Now, what odd, that depends on whether it is divisible by 3, divisible by 5, divisible by whatever number. And if it is in 10 digit and 100 digits, you cannot keep calculating one by one. So what we do, we say that as long as uh, we have a periodicity, no periodicity, dump it, it's over. If it is periodicity, then you put it into, so we already have factored that it is not a, uh, even though we have chosen a number n, we assume that that number is filtered out. It's not a even number, it is an odd number. And the second filtration is that it is having something periodic. It doesn't happen to be the n equal to n, and then you try. And so whatever that you bring other than that, if there is a periodicity, feed it to the periodic circuit and find what is R. If it is R is odd, then again you are not able to split. So again you have to repeat, choose another A. So this is a trial and error. Assume that you are getting odd, not odd, but R gets even, then you can say R by 2. So you can split with a plus minus 1, P minus 1, Q minus 1, as we said. So therefore we go with a R need to be even, and if it is odd, then we repeat with a new A. Otherwise we go with a number n and do a to the power R by 2, because R by 2, and it should give a mod 0 mod to n. That means what? It should be perfectly divisible to be able to get that. Mod should be 0. So that means that will give you the GCD as. So first we get the periodicity, then we determine it's a odd or even. If it is odd, then we go back. If it is even, then so if it is odd, no, that means it is even. So if it is even, then all we do is whatever A we chose the seed, that is a random seed which you took to take a crack at cracking the what you call the public key. N is the public key in this case, and you are trying to crack it. How many digit we don't know. At this time I am assuming whatever number of digit. So a to the power R by 2 should give you the mod 0, and therefore that is what we give. At the end of it, we conclude that a to the power R by 2 plus 1 comma n and a to the power R by 2 minus 1 are the factors of n. So cutting it short, all we are doing is we are trying to adopt a procedure which is the algorithm. The algorithm has a classical procedure as well as quantum procedure. So the Shor's algorithm of factorizing n into 2 prime is using the quantum Fourier transform or inverse quantum Fourier transform. Next slide. I think this significance is important to understand because the data encryption process usually generates a very big integer, n, which is the public key. So the public key, when you have keys which are P and Q, which are prime, so if you share this public key with anybody, nobody can crack that easily because so fast, because by the time computation happens, everything can be easily. So on the fly, you cannot generate P and Q with the n being large. And that is why the RSA algorithms today, what you are using, they are able to use 128, 256. Normal is currently 256 minimum. 512, it has gone to 512. It is going now. These are bits, okay? 256 bit, 512 bit, 768, and 1024 and 2048. So there are many numbers. And why do we care about the digits? Because 2 to the power n is our digit, right? Like if I have to describe 1,000 digit, then 2 to the power 10 I'll have to take. So that means I'll have to have minimum qubits of 10. But when you are having a number which are in 22 digit example we saw earlier, so for a 22 digit, we'll have to go 2 to the power to the 10 and 2 to the power 10. So we'll have to go 2 to the power 20 minimum. More than that. That means what? We'll have to have 20 qubit even minimum to even get there. And we are talking of thousands and thousands and billions of the 22 digits, which is what we saw. So if you have 100 digits, then what it will take? It will take more than hundreds of qubits. So to make sure that we understand, public key, which is n, which is factored as prime P and Q, is what we are trying to protect. And that requires heavy computation. Example, a 50 qubit might be able to break a 100-digit number. If we design well, if the Shor's algorithm designed well, but that is for what? For a 256 bit. Now, if you are using RSA of 4096 qubit, and that will be equivalent of 1200 digit number. So the more as we expect the quantum computing to come and crack our public key, we are going to go and go ahead with increasing the number of digits. But there is a limit to that, and therefore we have to change the algorithm. So these are all based on the what you call prime number factorization, and we can go for a lattice algorithm. That is the next. So instead of having a elliptical, which is what is used by RSA, this we are moving to a lattice algorithm where you have two-dimensional, so surface code rather than a linear code. So that's what we are doing, but encryption is the key, and Shor's algorithm is one of the ones which is likely to break sometime with the qubits increasing already, and that's the contention. Therefore, the use of Shor's is for encryption, and as long as we are not able to break it, we can continue for a few years. That's the expectation. Next slide. So what we found is that it is important to figure out what is the function. So normally what we do in quantum, when we define an algorithm, so we say that you have, because we have to depict in terms of gates. So if you take a function a and n of a x is your, uh, in this case we are talking of independent variable, that is your query. When you give a query input to a circuit, quantum gate, what happens is you are looking at variable x, and we are looking at the f of an of x is the function where a and n are both are parameters, whereas x is the variable, which is an integer. All three are integers, but we are trying to make sure that we are calculating for integer. So x is an integer, but it's a variable. So example, if I say 7 mod 2 equal to 1, it means what? 7 equal to 3 into 2 plus 1. Okay. So when we are factoring using modular operator, the mod operator is mod 2. So 7, if you want to do a mod 2, 2 into 3, 6, so only 1 is balanced. So balance of the operation of 7 mod 2 is 1. So the function returns a remainder of a raised to x divided by n. So that is why function a n into parameter x, into the independent variable x is nothing but a raised to x mod n. Let's take now another example, 21, to show this, how it works. Next slide. So if I say 21, I can choose any number, right? We know that we chose 2 last time. Instead of 2, we can choose 11, which is somewhere in between, but it is 11. So if I take f of 11, 21, 0, so what we have to do, a raised to x. A in this case is 11. 11 raised to 0, 11 raised to 1, 11 raised to 5, 6, etc. Now mod is always 21. So what you are going to do, you are taking a 11, okay, and raised to 0 is 1, so it cannot be divided, so it remains 1. 11 raised to 1, again you can't divide, so because 21 is still way off, so we just say 11, balance, remainder. We are only looking at the remainder, pattern of remainder, 1, 11. Next one we take 11 raised to 2, that is 11 11s are 121, and which is nothing but 21 into 5, 110, plus 21 into 5 is 115, right? And remaining whatever is there is 16 is what we are getting as reminder. So 11 raised to 3, again that number comes to 11 into 11 into 11, and so what essentially is whatever that number comes, we are saying 63 into 21 plus that number, and we are going with the pattern. So next one we will take 11 to the power 4, whatever that number comes out to be. You are again dividing by 21. So 21 into 697 plus 4 is that number. And this way we keep going, and then we find 1, 11, 16, 8, 4, 2, 1. So it has come back to 1. Next one we'll do 11 to the power 7. It will come up with another, which is 11. So basically 1, 11, 16, 8, 4, 2, 1. 1, 11, 16, 8, 4, 2. So this is 6. So that means what? What we see, the repeat factor is 6. So 11 F11 21 0 to F11 21 0 plus 6. That means if you start with number and then you go with, that is with 0 up to 6, that means it starts repeating again. So the repeat factor therefore is 6 for a simple number called 21, which we have taken as our factor, right? So for n equal to 21, we are getting r equal to 6. So now we can do the period is, it's computationally intensive, as you can see. So let's move on to now. We have taken 21 as the sample. Go ahead, next slide. Next. Yeah, okay. So now we are, before I get into shows into little more to complete, I'll just walk through in a brisk way. The source algorithm with fx equal to fx plus r, because r is the repeat factor, right? So f0 plus r, fx plus r, whatever that periodic function repeats by r, that is what we have to evaluate. So we can create a superposition of many arguments. That means what we have a and n, and whatever the number, we can evaluate the function exponentially with many arguments, whatever argument, and compute a parallel Fourier transform so that we can get the QFT period. And that once we get that, we can measure the power spectrum to obtain the period, and then we can apply the to the computation classical thing that we need. So let's just look at, instead of getting into these steps here, I will repeat the steps one more, but let's just focus on what is the quantum. So we said that for a function fx, it maps n bits of inputs to m bits. Mathematically, we say that f of whatever input string is there n times, and the output is 0, 1 m times. So in the case of Deutsch, we had a constant and a input string, whatever you give, you apply, and then output you get m string. So the total is m plus n. M being the LSB, n bits being, now we are talking of qubits, okay? Let me remind you, don't confuse this with just numbers. We are now talking qubits. So m ancillary we can use for measurement with a n actual which is playing in the game. So if you take a XOR quantum design, we had already said that if we want to apply on a n bits of x, then we need to have m bits of auxiliary to make it reversible. And the output function is nothing but whatever the query is xn in this case, which is nothing but this one, lower one, okay? Remember, I may use the n term and m term very often, so you'll get confused. Let me be very clear. N bits is the input query, and y equal to function of x, which is the output, and that is y exclusive or fx and fx of m, whereas x of n. So query input, what you give, this is the query, and when you do the ancillary to be able to store them, then whatever you get, this tensor product of n comma n to m, that is xn of ym, when you apply this unitary function, you get the xn y, xn and y exclusive or fx of m, which we had done previously. I am repeating this. We are going to use the top circuit. The bottom circuit is not we are looking at. This is the one which goes with MSB, LSB. This is the going with LSB, MSB. IBM Qiskit uses this, so we are going with this. If I assume this, then I have to say for the 21, which is 21 means how much? 21 means you got, after that number is 32. right? 2 to the power. If I say A is 2, example, 2 to the power 2, 4, 2 to the power 3, 8, 2 to the power 4, 16, 2 to the 5, 32. So if I say 21, I have to choose a n which is which is greater than 21. And therefore, if I choose 32 as a number, then 2 to the power n, which is 2 to the power 4, which is 16, and 2 to the power 5, which is 32, it is between 16 and 32, and that is the number n, which is our 21. So therefore, we will require how many qubits? So we'll require at least 5. That's what it turns out, right? 2 to the power 5, 32. So that means what? Now we have to make sure that somehow we put this into practice. So to store, we need m, and application of qubits, we require at least this much. So m plus n is what we need to take. So if you have 5 on the query side of it, which is x, then you also need at least 5 on the other side to store. So at least you will require 10. So what we do is we say that let's take n to n and m as n. So even though on the picture it is m and n, we are mapping of this quantum circuit for our use for the 21's calculation as we are mapping m to n, because that is what we need to control, and then we take n to 2n. So next slide. Now you will see how we are doing it. So basically we are saying our m is n, our n is 2n. That means we have circuits for a calculation of Shor's algorithm with the XROM quantum correct oracle circuit. What we have done is we have chosen by setting our m to n and n to 2n. So we are going to have n of this, that is 5, and this will be 10, because 2 and n is 5. This is 2 into 5, 10. So we will have 10 qubits here and 5 qubits. So we'll have 15 qubits, and then we can start. That's the way. But when you say 15 qubit, but still we'll have to worry about only the numbers here. So x, so our feeding of x is 2n, our measuring on x is n. So this is what is required now. Once you have understood what is m, what is n, in the sense of our m and our 2n. Why did we go to 2 to the power n? Because we know that we have to compute for 21, and we don't know how many multiplication and how many division, n number of things it will take. It depends on the number. So having taken 21, this is what is required. Now go to next slide. I will come back. So now you are seeing that our size z0, z, this is z, notation is z0. So z0 at the bottom shows is input of 0 to n times, and then tensor product with 0 n times. So when we start the circuit, the initialization psi 0, not psi, z0 happens to be 2n of 0 ket zeros and n of ket zeros. One is representing m, another, that is the left, is representing the n, and the right is representing m of our mn circuit, m plus n circuit. So that is 2n plus n circuit qubits. So xn is the query which represents fx, and ym are the auxiliary qubits. So now we have put it as fx and ym. So we need to add so many auxiliary bits because we need to store the result of fx somehow, right? So per qubit we have one at least per combination of qubits. So because XOR quantum, that is the requirement, and so we are going from ls bit to ms bit. So our y, which is y of fx, y exclusive are fx, and xn and y exclusive are fx of m, This is what we are trying to implement, this unitary matrix. Why do we need to do unitary matrix? We'll come to that, because initially we have to have whatever qubits you are given, you have to take a Hadamard of it and then provide it to the linear combination, and to be provided for a parallel computation, whatever it is. It could be 100, it could be 1000. All of that has to go into the what you call QFT to be able to identify the vector rotation angle, whereby we can do a what you call the constructive, and by able to determine the degree. Okay, so for n we require 2 to the power n greater than n, that is n equal to 21. So n equal to 5, so 2 raised to n is 32 greater than 22. So this I have already, so we need 3n qubits. In Shor's algorithm, we need 3n qubits, you remember? If you have n, so since we have n is equal to 5, 3n is equal to 15. So we will require 15 qubits, out of which 10 will be usable for the query and 5 will be the ancillary. And we start with step 0. Step 0, we define what is the input, initialization, size 0. Now go to next. And here we are talking Z1. Z1. So Z0, Z1, Z2, Z3, Z4, Z5. Those are the 5 outputs we have to measure. Gokhale, can you go back to the diagram once for, yeah, okay, good. So what you see is this is the initialization. This is the first output after Hadamard. This is the second output after applying the UF, and this is after applying the qubit, QFT, 2n qubit, because 2n are the inputs, and then we are trying to get the psi2, and when you apply, when you come to psi3, you get the product of q3, right? And then we go to psi4, where we do measure of the auxiliary, and we in psi5 we get the measure of the what you call the 2n inputs. So essentially what is important here is, this is summary of that. You got n and 2n qubits here, n qubits here. You are doing a this is only this portion, trying to represent the circuit, unitary circuit, which we have to do to get the angle from the QFT. We have to do a linear combination of all of these, and this is XOR quantum, which we had studied. How do you convert a circuit from a classical to a quantum? We should have reversible. So m plus n should be n plus m should be equal to um, both input and output, so that it is reversible. So we have taken 2n and n, and so only thing I want to point out is psi0 we saw what it is. Sorry, z0 is what we saw, which is nothing but all zeros. Z1, Z2, Z3, Z4. The Z1 is just after Hadamard, Z2 is after the unitary transform, Z3 is after the 2n qubit QFT applied. Then we are measuring, we know that we are measuring the phase. The quantum phase estimation Gokhale sir just showed you. So we are going to take both the LSB and for measurement for the n as well as 2n. Go back to the next slide. Next. So side 2. Yeah, so no, side 1, sorry, one more previous. So here we are, what we are doing? We are doing a Hadamard on the Z1 is nothing but step 1, and that is Hadamard and I for filling the other IN. So 2n and n. So you remember m is equal to n equal to 2n. That is the mapping we have taken. So we apply Hadamard to all the query, and then apply I to all. Identity means they are just for filler, so that you don't create any additional what you call, it's a null operation. And when you do this and then you apply zeros to it, overall you can apply all these at the end of it. What we get is important. That is 1 by 2 to the 1 by 2 raised to n, which is nothing. N is, in this case we have 5, So 1 by 2 raised to 5 of 2 raised to 2n is 2 raised to 10 minus 1. So basically what it means is so many gates we'll have to deal with. That's why we don't even talk about the 1 bit, 2 bit. We talk about m bit, n bit, m bit, and 2n bit. So essentially, we are taking 5 plus 10, 15, and all of the 15 we are wrapping up into power 0 to, because we have chosen n as 5 and 2n as 10, and that is why we are getting this. So you are getting x query input 2n and zeros, and this is nothing but normalization. So Z1 just gets a normalized what you call linear combination. Let's go to next step. Step 1 is Psi2. Now here you are applying the unitary XOR implementation, which is you get the Psi1 and get the Psi2 out of it. And to get Psi2, you just do again a multiplication of UF, and we had a UF which was defined as KTX for n bits and KTY for m bits. Our m and n, we know what it is. Our n and m is 2, m is n, and n is 2n. And that's what we are applying here. And at the end of the day, it is again coming out to nothing but across the tensor product of x 2n with a auxiliary f of x n and 1 by 2n. So this is, if you have, this is how many space C2 equal to n plus m. That means our C2 of n plus 2n, 2n plus n, that is equal to 3n. So we have got a 15, C15 here. C2 with 15. So that means what? Complex vector space for 15 parameters we are getting for a simple 21. Okay, go ahead, next slide. So now next slide, we take the Psi2, sorry, not Psi, Z3, Z2, and try to produce Z3. So which is nothing but quantum Fourier transform. So when we apply a QFT to the this one, we are simply saying that whatever comes on the 2, Z2, we are trying to get a Z3. So Z3 is nothing but UFT, we have to apply the QFT gate, and then n what you call null gates to ensure that we are taking whatever Psi2 was there, that last product what we got, and we are substituting that, and at the end of the day what are we getting? And uqft is defined as nothing but a summation or the omega matrix, right? Either the omega matrix 1 1 1 1 with omega 0 1 2 all that is unity. We had done the circle where we had done the unity of 12, right? So here it will be like 15, right? 2 to the power 2 and n is 5. So 2 to the power 10 is which is 1000, right? So 1 by root of 1000, k 0 to 2 to the power 2n, 2n is. So this is the assumption with the standard n. Now we have to apply with m and n as we had envisaged. And without getting into detail, I will say, like Gokhale had said, he needed a k. We are getting a k factor, omega k, because we are rotating minus k because we are going counterclockwise. So the rotation of omega 1, 2, 3, 4, how many degree we'll see that. But at this time, we know that we are looking at the rotation of omega with a k factor with the what you call the ancillaries of n. So you got n and 2m. So 2m, sorry, m and 2n. So 2n is here and 2n and n is our mapping. M mapping is this, n mapping is this. And n mapping is k. That means 2n qubits are here with k factor, and n qubits are there for the y, which is the fx factor, right? So this again divide by 1 to the power. So there are two summations which we apply, two rotations. And let's go to the next slide. You will realize now the rest 3, 4, and 5 are nothing but measurements. I will just simply put it this way without getting complexity into it. All we are doing is we are doing for x, x0 to yr and k0. So basically what we are doing is we are working out for omega k rotation, and then applying what you call the summation with x0, and our factor is r is the repeat factor, right? So what we are trying to get is we are trying to get the repeat factor by applying the k and see what is the repeat factor and whether that repeat factor, because we know that we are trying to figure out how many rotations, how many periods will be there, r will be there before we can come to x0, right? To xr. So we had said f of x0 equal to f of x0 plus r, right? So that r factor is what we are going to determine using this step. Without getting into mathematics, this is just a measurement of the z4, and same way z5 is the real measurement where we get the k factor. So those 4 and 5, z4 and z5 are nothing but measurement of the uh, MSB and the LSB and the MSB. So I don't recollect whether MSB or LSB, but we have both measurements. Can you go back, quickly to that diagram just to check whether I'm, which was the, yeah. So LSB measurement is first, MSB. So 4 is for the LSB and 5 is for the MSB. MSB is the final one. Yeah, go back. Correct. So it is order is LSB, MSB. And so what we have, yeah, go back to Z5. And so this is the one which is the final measurement where we will get the rotation, and that rotation we can easily figure out based on what the K factor is. Go to the next. So 4 and 5 are just simple measurement. Here you see the imaginary axis and the real axis. So here 2 pi k0, that r factor, repeat factor is there, divide by 2 to the power 2n is 2 pi d, and r is equal to 2 to the power 2n d by k0. Now this is a little bit odd, but simplify, put it that we have got yellow and red. Okay, so our factor which is there is that what do you call Euler's number, which is 2.148, we use for rotational of any of the vectors in the unit sphere. This is virtual. So C15, C2 15, C2 into 15, that means this is around C2s of 15. So you are going to get 15. So division of 180 by 15, whatever that comes out to. No, not even that. We have to go by 2 to the power 15. So what it means is the angle which is there, like example 0, when yellow ones only follow, y0, y1, y2, y3, y4, y5. Then after this 0 to 5, it comes to y6, and you are saying you are repeating. So this is the one which is establishing the repeat, y6, y7, y8, y9, y10. So what it means is this e to the power minus I 2 pi k0 yr by 2 to the power 2 raised on the complex plane, yellow dots refer to the first round and red dots refers to the second round. So one round and two round, we say we know that it is repeat factor is established. And then what we do is you look at the right side, which is your y0 and y1. So distribution of the resulting is constructive interference. If you go at y0, y1, that is the one which is we are trying to show here. So basically, repeat factor is important, and that is what it should result in. Now, it's highly complex, and plus the number of qubits is beyond what we had in the IBM quiz kit, I believe, to really effectively implement. So, and plus the changes have occurred in the what you call IBM quiz kit, and we are unable to really do practical demonstration of this. Go to the next slide. But summary, no, go to the summary slide, sorry. So what we have done, we presented first the quantum phase estimation, and application of that we have used in the Shor's algorithm with the classical GCD with n arguments. And obviously when you got so many qubits requirement, it is just not easy to demonstrate. We will see what we can do. If we can record, we will keep it for the you to go over it. But you can go over the assignments here, and then with that, I think, come to an end. Gokhale, next slide, and you can take over. Yeah. So we have with that, what we have is phase two, and it's simply we know. Go ahead, Gokhale.
Okay, hello. Thank you very much, Prakash. So, what we will be trying to do is, we have got some issues like in the sense that the IBM QuizKit, one of the library that supports Shore's application. So, we've got QuizKit.application, that's a module, and that particular module got upgraded as recent as August end, and that is not actually getting integrated well with my notebook, so I could not demonstrate because it's throwing a whole bunch of errors. I'll try to resolve that, and then I'll put up the source demo implementation, and probably we'll just record a small session and then keep it up there, right? And see, what we have done so far, I believe, is just only the ground fundamentals about what quantum computing is about, what exactly is the notation, what exactly we mean by quantum states, what is meant by measurements. We have identified a few basic gates, their operations, and then quickly assemble a small circuit and use this circuit for some very, very elementary quantum algorithms. Right? The algorithms which you have seen are basic algorithms. So, what myself and Prakash were discussing yesterday was that we will just probably try to come up with a separate another sort of a interaction session wherein we can only concentrate, take off from here, only concentrate on identifying a bunch of algorithms pertaining to some specific domains, maybe a domain about signal processing or image processing, or maybe get onto this encryption or linear algebra or machine learning and stuff like that. So I'm planning to identify a whole bunch of application areas, and then we will now primarily focus on devising algorithms, and then we'll try to run a bunch of interactive sessions maybe after 4 weeks from now, 4 to 5 weeks from now. Announcement will be made by Prakash. And as far as the Shore's implementation is concerned, details would be sent down to you, and in the form of a notification. We will record a small session and then keep the recording for you open. The other thing which is also needed to be done from my side is I will pick up all the examples which we have discussed so far, and then I will dump them accordingly into the respective folders on a per session basis. We have already done something like 18 sessions we have done. So into each of this particular session, we have got the PowerPoint presentations, and I'll also put in the IBM QuizKit implementations. In some cases, it could be a notebook, or in some cases, it could be the visual application itself, right? Through the IBM Composer. So I'll just dump all this, and then we'll keep everything ready. So maybe just give me a couple of days, and then that should be ready by then. And what I request all of you is, if you can just quickly give us some sort of a feedback in terms of what should be done and how it can be done better. And in addition to that, also if you can just let us know what are the lessons learned from all these 18 weeks of interactions. I think we will be pretty glad, and we will feel that the objective is from our side is met. So can I request participants please to unmute themselves and then uh, give us their bouquets or brickbats, I should say. That would be a very nice interaction. Maybe towards the end, we have about another 5 to 10 minutes. Can I request uh, Thomas, Sam, Kevin, Matto,
Hello.
Evie, and yeah.
Excellent. I really like the content and the whole structure that the mathematics is separate and then the coding and the Qiskit is separate. That shows a different sides of the problems. I was thinking about also that there's different kinds of implementations of the gates, like the imaginary Toffoli or imaginary swap or the square root of swap. But those are very like specific cases, but would be interesting to hear maybe in the future something like the use cases to use the specific or special gates.
Yep.
I think
Thank
that's
you.
it.
Yeah. Thank you, Thomas, for this wonderful input. I think we will just look into that and then try to incorporate that in maybe the subsequent session. Yeah. Thank you so much. Thank you so much. Yes, I
Thank
think
you.
Kevin. Yeah. Thank you so much, Thomas. Kevin, can you add a few words from your side?
Yeah, obviously I'm coming from the QML perspective, and it's definitely with circuits and data set mapping, as opposed to much entanglement, these types of things. So we need new architecture in neural networks, quantum neural networks, and then we also more parameters. And that's what will keep driving the industry forward at this time, especially with QML.
Super. Very frankly, we have not really taken a very hard approach even into coding. We have stuck to some very elementary preliminaries, and we have also ensured the fact that we have taken more or less the codes which are freely available, so that in case someone would like to refer back after the session gets over, don't have to really grope around a lot of places. So that is one of the reasons why we have done that. And getting on to maybe even at an assembly level, Quasm implementation is something that we can also typically focus. And then obviously the next option looking forward would be getting into maybe implementing a bunch of these QML machine learning algorithms. Let us just maybe run a separate bunch of sessions purely on QML, and the focus out there would be on neural nets, and or maybe focus would be on, let's say I got your TensorFlow. How can we just have this TensorFlow examples getting mapped onto the quantum domain? That is something which also would be very, very interesting, because that is where a lot of applications are presently getting focused on. So I'll just surely keep this in mind, and then let us see how we can just work backwards in the next 4 to 5 weeks. Next 4 to 5 weeks will be a lot of hard time for us trying to make a separate, slightly advanced level module. No, it should not be just 101 now. So we'll be just moving on to the next stage. Thank you, Kevin. And in case you have any additional inputs on these lines, I request you to put up a small mail to Prakash, and we will consider these inputs and then try to incorporate in the subsequent interactive sessions.
Yeah, I appreciate it.
Yeah, thank you so much. Thank you.
Oh, Vishwa disappeared. I wanted him.
Yeah, he just maybe lost connection. Can I request Matthew to please unmute and maybe give a feedback? Is Matthew around? Or may I request Sam?
Yeah, anyone wants to unmute?
Anyone wants to? Yeah.
Or you can put in the chat window.
Okay, Matthew had one small query, like where could we locate the PPT slides. Prakash, you can just address Matthew later and then send him a mail about the link where he can find the PPT slides.
Yeah, I put a link, but I can.
Okay, yeah, do that.
I can do one thing. There is an open tech forum where we post the slides, and this is the link for it.
Oh, yeah, you can put the link in the chat box. Yeah.
Yeah, OpenTech Forum at OpenTech Forum forum 1140 without any dot, and this is on YouTube. Uh, Additionally, I want to add something which Kevin was mentioning as well as Thomas, that we covered only gate-based quantum. We did not do anything on adiabatic quantum, and a lot of uh, industry folks have been using QAOA and QBO and kind of algorithms which are more associated with adiabatic quantum, including the financials and all. So that portion we have missed. Maybe we'll cover it next time in next series, because we did not want to cover anything on adiabatic because we did not have right what you call curriculum to follow. Plus, here also we just adopted whatever was there as per book, because sometimes it is difficult to put it on the board. Even today I had done that. What is that? We have tried various boards and all this to be able to draw, but that's something, writing a notation Z or a pi, and all the gates are also available in this board. There are other boards also we have used. We have tried various techniques, but it is very difficult, and therefore we had to adopt the book. Beginning itself, we understood that trying to use a Greek Latin terminology and mathematical on a computer with our limited resources, we were constrained by that. So see what we can do about it. At least we have found a way to express ourselves. That's at least working for everybody, and hopefully the public resources which are available you can use. Besides, so we had one Susskind's book, we had one of the Gate books also, but adiabatic quantum we did not do have a good book to. Actually, we have not gone through to say that this is the right thing at this time. So that was the reason. So I think Gokhale, Sam, and Matthew, and if they don't have anything, Kevin has already said what he wanted, and we will consider his feedback very properly, and so with Thomas. And those who want to add more, please go ahead. And I think we should end the session. Gokhale, what do you say? Gokhale, shall I? Oh, Gokhale has disappeared already. Okay. So Matt, Sam, Kevin, and Thomas, I will try to close the session. Gokhale, I want to end the session. Is that okay with you? Do you have any last word?
No, Gokhale. Yeah, Prakash, thank you so much. And thanks everyone on all the participants. Thank you for your support.
And
It
Kevin,
was
what is that?
actually indeed a learning experience for us. Yeah.
Okay. So Thomas has, sorry, Kevin has put some link on the chat window. I'll take it.
Yeah.
I'll just copy it and then use it. And rest of it is also available to us. So I'll stop the recording here.
Okay. Thank